Let's see one more use of logarithms. So we're used to finding the equation of lines, or at least the gradient of lines, in the form y equals mx plus c, or alternatively ax plus by plus c equals 0. And we know we can find gradients in that form or through differentiation. But let's say that we've gathered some data, so we have a collection of points, and it looks something like this. Okay, so looking at that collection of points, we can't differentiate to find the gradient of this or find out what function this is, as we can't differentiate a series of points. All we could do is find chords between 2 points. We may look at this and think, well, I'm not entirely sure what this function is, but it appears to have the form something along the lines y equals a lots of some number b to the power of x. So we think it's some sort of exponential function, something like 2 to the power of x. And we suspect that that's what our function looks like. Well, if that is what our function looks like, how can we find the values of a and b for some variables x? What we're going to do is we're going to take logs of both sides. So let's just do log. If I don't write a base, I imply base 10, log y, and I'm going to take logs of this side as well, log a b to the power x. Okay, this doesn't look very helpful yet, but again, what I can do is I can now use my log rules. So remember, before I can use the power rule, because a is not to the power x, I need to split up this multiplication. So if we recall, we can write a multiplication within a logarithm as the multiplication of 2 logarithms. Therefore, I can write this now in the form x log b plus log a, and that will be log y. Okay, so why have we done this? What we've done is we've taken our original exponential function, something which, or at least what we think is an exponential, would look like that, and that would be our y-axis and our x-axis. And what we've done is we've transformed it into this form, which now has a log y-axis and a log and a x-axis, sorry. If we look there, x is not inside a logarithm, so this is still just an x-axis. What will this graph look like? So we should know, if we take logarithms of an exponential, it just becomes linear. If we look at that, we have our log y-axis here, and then we have something which is of the form x times a constant. Remember, b, we don't know it yet, but it will be some fixed constant, plus log a. Again, a will be some fixed constant. So this is now of the form log y is equal to, that is our mx, and that will be our plus c. So looking at this, we will have what we call linearized this graph. It will now be some straight line. So we get a collection of points which lie on or close to a straight line. Remember, this would be from collecting some data, so there may be some natural variation in this, but generally speaking we'll have at least a line of best fit. And now we draw parallels between our y equals mx plus c and our function that we've derived here. So looking at this, this is our plus c. We know that the y-intercept would be log a. That will be our y-intercept. Similarly, if I look at the gradient of this line, so remember, you want to be accurate here, so you want the biggest triangle possible. Finding the gradient of this line, that will be our m, and m will equal log of b. So that's the idea. We're going to take an exponential graph and we're going to linearise it so that we can look at stuff in terms of y equals mx plus c, or at least log y equals mx plus c. Noticing that our log a is our y-intercept and m, our gradient, is log b. Okay, so let's look at an example of that. Let's say that we're given a graph and we are told that this graph has a y-intercept, or a log y, sorry. A log y-intercept of 0.37. And let's say that this graph has a gradient of, so m is 1.2. Like we said before, we may have to find this line, or we may have some points, and it may be on graph paper, so we can calculate our change in y over change in x, and we could also just look to see our y-intercept if we're given an accurate graph. Okay, so recalling that form, we suspected it was originally of the form y equals a b to the x, which we derived meant that log y is equal to x log b plus log a. That is our gradient, m. And this is our plus c, our y-intercept. Okay, so now that we know that, we should be able to just do b is equal to 10 to the power of 1.2. Remember, if we can't see a log base, we assume it means log base 10. I'm just going to put that in my calculator. So I have 10 to the power of 1.2. That gives me 15.85. And then here I'm similarly going to do 10 to the power of 0.37. And that tells me that A is equal to 2.34. Okay, so once we've done all of that work, we can now write down the original equation. So we'll just clear this board quickly. We suspected it was of the form y equals a b to the power x. Now that we know our a and our b, we know that the equation of this line is y equals 2.34 times 15.85 to the power of 1.2. Sorry, to the power of x. Okay, we have our equation. That is the model that we can use to predict whatever the context to this question was. In the next video, we'll look at a slightly different form where we have equations that we suspect are of the form y equals ax to the power of b. So this time we suspect that it's x which is being raised to some unknown power. Perhaps we think it looks a little bit like a cubic, but it could be to the power 5 or power 7, or indeed it could be something between. Maybe it's some decimal power. B could be 3.27. We'll look at how we do that in the next video.